So this is a reminder, Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and please participate, but please do not share personal information for your own security reasons. All right, guys, you are in the live class, so you should go ahead and open up that link that I just put in the chat box. Go ahead and enter the password as well. Remember, you have to spell it exactly as you see it, and same with capitalization. Make sure the first letter is capitalized. Go ahead, enter that in, and click Start Quiz to get your attendance ticket started. You don't have to do anything with it yet. Just have it open and ready to go. I will be giving you the answers throughout class. And remember, those will also be the same questions that will be on your quiz. So doing your attendance ticket is super helpful because it has the same answers as your quiz. Remember, if you're watching the recording, you don't get the password. Password is only provided in live class so that you can get your 10% of attendance in the class. Awesome. Okay, so we are officially in week 4, guys. Do you guys remember how many weeks there are in the entire quarter? There's probably less than you're thinking, right? Awesome, awesome. Yeah, there's only 10 weeks in the quarter, guys, and we are already in week 4. Okay, go ahead and give me a smiley face if that makes you happy, right? Hopefully that makes most of us pretty happy. Yep, it's going by quickly. All right, awesome. So, so remember, guys, that we do have 10 units in this course. Oh, silly baby, I'm not ready for those slides yet. We do have 10, let's see here, 10 units in this quarter, which means we go through one unit about every single week. All right, this week we're actually going to finish all of unit 4 in 3 days, and then we're going to go ahead and start on unit number 5. So we're going to be talking about pressure and buoyancy today. Tomorrow we'll talk about Pascal's and Bernoulli's principles. Wednesday we'll have a game day, and then Thursday and Friday we will be starting our energy unit for unit number 5. Lucky you guys, you don't have any labs this week, so I definitely say that if you need to, make sure you catch up on all of your labs. Remember, those are 25% of your grades. You want to make sure you are getting those done. Yeah, I like game days too. Awesome. Okay, so we are talking this unit. This is unit number 4. We're talking about fluid forces. So we're going to be taking a look at some forces with fluids and pressure. We'll talk about pressure, shape, and density. And then we'll also talk about Pascal's and Bernoulli's principles, which have to do with hydraulics and how airplanes work. So we'll talk about that at the end of our unit. So today we should be able to define pressure, density, and buoyancy and describe the effects that temperature, volume, and depth have on pressure. And today at the end of class you'll be working on the 4A quiz. Should be a pretty quick one. It's only 6 questions, and again all the answers will be from the attendance ticket that you fill out. So today we're going to talk about a little bit of what pressure is, and pressure changes with temperature, volume, and depth. So let's take a look at that. First things first, here is what pressure is. Pressure is when molecules collide within a fluid, which creates or changes pressure. So how many of you guys have ever done this? For example, with your little siblings, you've been playing with a hose and then you put your thumb over the nozzle and then it goes really, really fast, really far, and you knock your siblings in the face with that. Smiley faces if you guys know what I'm talking about. Yeah. All right, yes, definitely a little bit. That's pretty funny, right? So yeah, this right here, this is what's called creating higher pressure. All right, so if you put your finger over the nozzle of a hose, you're going to create a lot higher pressure, and the water is going to shoot out what? Faster or slower? Will the water shoot out faster or slower? Tell me in the chat box. What happens when we put our finger over the nozzle of a hose? Yeah, much, much faster. So higher pressure, what we're going to see is that's going to create more and more collisions, which makes things move faster. Okay, so pressure is caused by the weight and collisions of a fluid's molecules against the surface of the container. So this is really important to understand, guys. When I talk about pressure, really what I'm just talking about is collisions. Okay, so pressure is the same thing as talking about collisions. Smiley faces if that makes sense. Okay, this is really important. We're going to talk about the word collisions a lot throughout this unit. So it's really important to understand what that means. Okay, so we can see this right here, for example, that under high pressure, when we have our finger over the nozzle, what happens is you're making all of those molecules push against each other and collide against each other way more, as well as against the container. And so because they're just hitting each other so much more, that creates a huge amount of force, which is why the water is able to kind of burst out of the hose so quickly. Give me a thumbs up if that makes sense. More collisions, more pressure, a lot more force. Excellent. Okay, this is number 1 in your attendance ticket. I see lots of you have given me green checks, but continue. I'm going to go ahead and give you guys 20 seconds to work on that. Please enter collisions into your first blank. Ready, set, go. Just waiting on a few more green checks. So April, make sure I get your green check. Haley, Jake, Miranda, Melissa, Seja, and Deepak, make sure I get your green checks, please. Yeah, we kind of double up on labs for the next unit, so that's why there's no lab during this unit. Awesome. All right, let's keep on going, guys. Okay, so another way that we can think about this, all right, is that when we're talking about pressures with fluids or fluid forces, this includes more things than just like water in a hose. So a fluid is anything that flows. So remember, we talked about when we're biking, air kind of flows around us. Smiley faces if you remember that. Air flows around us. Smiley faces if you remember that. Yeah, so for that reason, even gases like oxygen and carbon dioxide, even gases in the atmosphere are also fluids. And we know this because we talk about air pressure all the time. Think about if you've ever had to try to pump up your bike or pump up a car tire. Okay, what are you pumping it up with? What fluid are you putting into those tires? Tell me in the chat box. What fluids are we putting into those tires? Yeah, we're putting air into them, exactly. So air is a fluid that is creating pressure. Okay, so again, what we're seeing here is that air pressure is just the force exerting on the edges of the tire, the inside of the tire, by the weight of that air. Okay, so let's go ahead and talk a little bit about things that can affect pressure. So the way that we can affect pressure within a container is we can change how much fluid there is. We can heat or cool the fluid, or we can increase or decrease the container. Okay, so what I want you guys to think about this here is that if you were to increase the amount of molecules, just like you're increasing the amount of air in a tire, that's going to increase our pressure. That's why we add air to the tire. Smiley faces if that makes sense. You're adding air molecules, that's going to make more pressure. That's what's blowing up your tire. Excellent. So think about it this way, guys. If you imagine that you are in a room, okay, and you start out with 5 people, okay, walking around in that room, is there a big likelihood of you running into anybody else? There's only 5 of you in a regular sized room walking around. Are you going to run into other people? Tell me what you guys think. If there's 5 people in a room and you're walking around, okay, let's think about, okay, we may need to think about what kind of room we're talking about. Let's say that we are talking about a gymnasium. All right, let's say we're talking about a gymnasium. There's 5 people in there and you're walking around. Are you going to run into them? No, definitely not. Now, let's say I suddenly try to increase the amount of people. I'm adding a lot more people or a lot more molecules. So now let's say I try to add 5,000 more people into that gymnasium. Are there going to be more people that you run into? Do you think there's going to be more collisions if you add 5,000 people? Yeah, think about when you're in a crowd, you're touching somebody, right? Most of the time there's somebody that is nearby you, and if you try to walk around, you're going to have to run into them or at least, pat them on the shoulder and go by them, right? So when there's way more molecules, you're going to end up with way more collisions, and so that's going to increase our pressure. Remember, collisions equals pressure. Smiley faces if that makes sense. Collisions equals pressure. Excellent, looking good. Okay, so now let's go back to our gymnasium. Let's say now we've got just a class, right? So let's say we've got 100 people in that gymnasium. Okay, now first off, if they are all nice and cool, meaning that they have They're just walking around. Nobody's really warm. They're just, walking around slowly. Are you going to run into anyone? 100 people in a gymnasium, right? They've each still got enough space, walking around nice and cool. Are you running into anyone? Are you running into anyone? All right, guys, I need a little bit more participation in that chat box. Again, I'm asking if we have 100 people in a gymnasium, all right, and we're just walking around nice and slow, staying nice and cool. Are you going to really... What? No, you're not running into people, guys. Okay? 100 people in a gymnasium, that's not that crowded, guys. It's not very crowded, and if you're walking around, you're not going to run into anyone. Smiley faces if that makes sense. Smiley faces if that makes sense. Awesome. Now what I want you guys to do is I want you to increase the temperature. So suddenly those people are going to get really warm by sprinting around. So if we have 100 people sprinting around randomly in a gym, do you think that that's going to increase the amount of collisions? Okay, we're getting hotter and hotter. They're sprinting, getting warmer. Yes, definitely. So what happens here is as you increase temperature, molecules do the same thing. They have way more energy, they start sprinting around, and so that means more collisions, therefore more pressure. Okay? So again, if you add more molecules, add more people, that makes more collisions. If you increase their temperature, make them run around faster, that increases pressure because of more collisions. And then the last thing we need to talk about is what happens if we increase the volume. Okay, so what I want you guys to think about again is go back to our normal gym, okay? Let's say that we've got 100 people, or sorry, let's say that we've got a crowd in that gym, right? We've got 3,000 people in that gym, okay? Now we're going to actually increase the volume. So let's say that we take that gym and we turn it into a stadium. Okay, if we turn it into a stadium, even with a lot of people, do you think there's going to be more or less collisions? Okay, if you turn it into a stadium, you give everyone more space, are there going to be more or less collisions? Yeah, definitely less collisions, okay? So volume is the only one that's backwards, where if you increase the volume, that means you give everyone more space, and so there's less collisions overall. Smiley faces if that makes sense. You can actually see that right here. If I increase the volume, there's going to be less collisions. All right, perfect. All right, guys, hold on one second. Perfect. All right, guys, that looks good. All right, let's keep on going. So let's make sure that this makes sense. So we're going to go ahead and match up the term on the left with the definition on the right. So take a look at all of these different situations on the left. I want you to think about, are there going to be less collisions and therefore less pressure, or more collisions and therefore more pressure? Go ahead, match those up on the whiteboard. Use your whiteboard tools. Let's get started. Let's work. All right, and we're pausing in 5, 4, 3, 2, and 1. All right, let's go ahead. I'm going to clean this up on our whiteboard so that we can go ahead and see the correct answers up here. Looking good. Oops, sorry. That's not what I meant to paste. I'm so sorry. Here we go, Jasmine. Here you go. All right, so let's go ahead and get the correct answer up here. Let me grab the whiteboard tool here. All right, so more molecules. We know that if we try to stuff more people into our gym, that's going to increase the collisions, and therefore that is more pressure. The opposite is then true, right? If we get rid of a bunch of people in that gym, right, we're going to decrease the amount of collisions and therefore decreased pressure. Awesome. Looks like we really understood that one. Higher temperature, right? You start sprinting around. All the molecules are moving a lot faster. That is definitely increased collisions, right? We're sprinting around. If we lower the temperature, on the other hand, everyone's moving much more slowly. We're going to decrease the amount of collisions and therefore less pressure. Now this one we seemed to be a little bit split on. All right, so again, larger volume. Does that mean that those molecules have more or less space to move around? Larger volume. Do they have more or less space to move around? They have more space. Okay, if you increase the volume, you go from a gymnasium to a stadium. That's way more volume, way more space. And what does that mean, guys? More or less collisions? More or less collisions? If we increase the volume, give them more space, all right, are they going to run into each other more or less? Yeah, definitely less. So this would actually decrease our collisions, and therefore we would have less pressure. Whereas if you try to stuff those 1,000 people into a closet, that's definitely going to increase our collisions and therefore increase our pressure. Smiley faces if these last two make sense. Remember, volume is the one that's backwards. Volume is the one that's backwards. Has a different pattern. Awesome. Okay, this is number 2 in your attendance ticket. I'm going to go ahead and give you guys 60 seconds to work on that since it's a little bit of a longer one. Give me a green check when you have this saved. Green check when you have number 2 saved. Make sure you match it up correctly. Excellent. Just waiting on a few more green checks. Adrian, Andrew, Annalise, Audrey, Ciara, Dalen, Jasmine, Johnny, Miranda, Melissa, Seja, Sophia, Tyson, Zoe. Zoe O. Make sure I get your green checks. Remember, if you ever are having trouble with your attendance ticket, you can always take a picture so that you have it for later. Looking good. Okay, guys, so the last thing that we need to talk about is just that when we talk about pressure, pressure actually uses real numbers, right? So we can talk about pressure kind of mentally talking about more pressure, less pressure, but in reality, there's actually a little bit of math behind this. So what pressure is it's force divided by area, or we could say it as force per unit of area for how much area there is. Smiley faces if that makes sense. When we say divided by, that's just another way of saying per. Just like miles per hour is actually miles divided by hours. Perfect. Okay, so here's the thing. Let's say that we have a heel, a high heel, and a sneaker right here. Okay, so a high heel, tell me, looking at this part right here, does this have just a little bit of area or a lot of area? Seja, it's in the main chat box here. I can paste it here too. Yeah, this has very, very little area. This is a tiny, tiny little bit, right? So this has very little area, whereas our sneaker has a lot of area. Okay, smiley faces if you guys can see that. Heel has a little bit of area, sneaker has a lot of area touching the ground, right? Okay, perfect. So let's go ahead and actually figure this out. So let's say that this person right here, okay, has a weight of 100 newtons. So this person is wearing, right, a heel on one foot and a sneaker on the other foot. So the same amount of weight on either shoe, right? Because the person's going to weigh the same. So on the sneaker, right, we have a force or a weight of 100 newtons. Okay, and with the high heel, same thing. We have a force or a weight of 100 newtons. Smiley faces if that makes sense. This is our weight slash force. This right here is our weight slash force. And so the person obviously weighs the same. So we're going to use the same number to start us off. Now we need to divide by the area. Okay, so let's say that our sneaker right here has an area, okay, of 0.1 meters squared. And the high heel has a much smaller area of 0.01 meters squared. Okay, so this is what we're going to go ahead and plug in to the second part for area. Okay, so we're going to plug these numbers in to the second part for area. So underneath the sneakers area, okay, I'm going to enter in 0.1 meters squared. That's what I said the area of that sneaker is. And under the high heel, theirs is much smaller, right? 0.01 meters squared. Smiley faces if you guys are following along with what I'm doing here, if this is making sense. Shh, 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 shh. Awesome. Okay, so we need to go ahead and actually do this math. Go ahead and plug this into a calculator. 100 divided by 0.1. What does that equal? 100 divided by 0.1. What do you guys think? Go ahead, plug that into a calculator. Get me an answer. Again, you can use your phone or your computer calculator, or you can Google the word calculator. What is 100 divided by 0.1? Yes, you guys are absolutely correct. Yep, this is going to be 1,000. Yep, and our unit for this is going to be what are called pascals. Okay, 1,000 pascals. Okay, so we can see that's the pressure for our sneaker. Now, what about our high heel? Do 100 divided by 0.01, right? This is much, much smaller of an area. Remember, our high heel has a very small area. What happens to the pressure? What does the pressure equal? Yes, it's way bigger, guys, right? This is 10,000 pascals, right? This is 10,000 pascals. Okay, so let's think about this. With a high heel, if I have a little bit of area, does that make a low pressure or a high pressure? Does that make a low pressure or a high pressure? Yeah, we just calculated it. Yes, this is a much higher pressure. Whereas our sneaker, because it has a lot of area, actually has a much lower pressure. And we know this in real life, guys, right? Would you rather be stepped on by a high heel or by a sneaker? If you had to choose one, which would you prefer to be stepped on? Absolutely the sneaker, right? And the reason for that is because the sneaker actually takes that force and distributes it over a very big area, so you don't feel it quite as much. If you take all of that pressure and try to put it in a tiny little spot, that's going to hurt because it's a much higher pressure. Okay, so there's a really cool experiment that demonstrates this, that if you have a lot of area, you can actually prevent a lot of pressure in a single spot. So let me go ahead and I'm going to paste this in your chat box as well as put it on the whiteboard. All right, it's about a minute long. Give me a green check when you finish watching it. All right, so what did we just see happen? Tell me in the chat box, what did you just observe, guys? Isn't that crazy? I know. Yeah, you should try it at home, but maybe do it outside. Exactly. Yeah, they were walking on eggs without the eggs breaking. Now, think about this, right? The person, okay, weighs a lot, but they're kind of distributing all that pressure over how many eggs? How many eggs were they spreading that pressure over each time they stepped on a carton? Yeah, over 12 eggs, right? So they were spreading out all of their weight over 12 different eggs. And so in the end, none of the eggs broke, right? Because we were spreading it all out. Now, what happened if that person was wearing high heels and put all of their weight on a single egg? What would happen if a person was wearing high heels and put all of their weight on a single egg, just with their one heel? Yeah, they would totally crack, because if you take all that pressure and you all just put it on a single egg, a single spot, that's a lot more force in that single amount of area than it is being spread out among 12 eggs. Smiley faces if that helps you better understand this concept. That with more area, there's less pressure. With less area, there's much more pressure. Awesome. Okay, guys, this is number 3 in your attendance ticket. Go ahead and give me a green check when you have it saved. All right, go ahead, give me a green check. April, Ariana, Audrey, Ciara, Dalen, Dolly. Let's see here. Haley, Jake, Jeremy, Johnny, Miranda, Melissa, and Steven. Go ahead, give me a green check if we have number 3 saved. All right, Dolly, if you're having an issue, you can let me know in the chat box, or you can take a picture of it and just make sure you have it for later. Awesome. Okay, I do see you're typing. Okay, perfect. Good to know. Awesome. All right, let's go ahead and keep on moving. All right, so the last thing that we need to talk about is buoyancy. And what buoyancy is basically it just means the amount of floatiness that something has. Okay, so buoyancy means the tendency to float or sink. And what it depends on is the density of an object versus the density of a fluid. All right, sorry guys, can you hear me? Okay, so it's going to depend on the density of the object versus the density of the fluid. So what this means is that if a density of an object is less than the density of water, then the object is going to float. And we're going to talk a little bit about what density means, but basically what density is With a given amount of space, it's how heavy that object is in that amount of space. Okay, so we can see here, right, that if it's floating, that means that it's less dense. If it's sinking, that means it's more dense than the water. Okay, so first off, let's talk a little bit about what density is. So density is how closely packed the particles in a substance are. Okay, so right here. So the way that we calculate this is we take the mass of the object and we divide it by the volume of the object. Which remember, space is just the volume is just the amount of space that an object occupies. So we can see that equation right here. Density equals mass divided by volume. Smiley faces if that makes sense. Smiley faces if that makes sense. Density equals mass divided by volume. Okay, perfect. So let's think about this. A tennis ball and a baseball, right? They are about the same size, which means they have the same what? Do they have the same mass or the same volume? If they're about the same size, they take up the same amount of space. Am I talking about mass or volume? Yeah, I'm actually talking about volume. I'm talking about the amount of volume. So a tennis ball and a baseball have the same volume, but a baseball feels heavier because it's much denser, meaning that in that amount of volume, it has way more mass. Okay, it's much more tightly packed. So we can see that here, right? That when we spread out the molecules, we're going to be very much less dense. When we pack them in really tightly, we're going to be much more dense. Okay, so even though all of these boxes have the same volume, meaning they're all the same size, right, their density depends on how many molecules we're stuffing into that space. Smiley faces if that makes sense. A baseball is heavier because we're stuffing in more molecules into that space, even though it's the same size as a tennis ball. Awesome. Okay, this is number 4 in your attendance ticket. Give me a green check when you have that saved. All right, just waiting on green checks from Andres, Annalise, Audrey, Ciara, Dolly, Johnny, Miranda, Melissa, Tyson. Make sure I get your green checks for number 4. Good, guys. Oops, sorry, that's not the right thing I wanted to paste. My bad. Here's the link. Here we go. All right, looking good. Okay, so here's what we're going to talk about. So the principle of flotation says that an object will float if it's less dense than water, right? So if you look at this cup right here, okay, if I have an object that's at the top of the cup of water and it's floating above the water, part of it's above the water, then it must be less dense than water, meaning that the amount of space it takes up, it has less molecules in that space than water does, okay? Now, on the other hand, an object is going to sink if it's much more dense than water, meaning the amount of space it takes up, okay, is going to have way more mass than that of water. Or if an object is suspended in the center of water, then it must have the same density as water, meaning the amount of space it takes up is actually the same as the amount of space it takes up has the same mass as that of water. Give me a smiley face if this makes sense. You can see this diagram here. Smiley face if this diagram makes sense. Okay, so this is really important to know, guys, though, that it has to be a relationship between mass and volume. Density is both mass and volume together because the mass alone of an object does not matter, right? If you think about a cruise ship has a lot of mass, but does a cruise ship still float? Even though a cruise ship has tons and tons of mass, is it still going to float? Yes or no? Hopefully it still floats, right? So that's not what matters. What matters is its density. So a cruise ship is so big, but a cruise ship is mostly empty space. So since it's mostly empty space, it actually is less dense than water. Smiley faces if that makes sense. A cruise ship floats because it's less dense. Even though it's much, much heavier than other objects, it's still going to float because it's mostly empty space. Awesome. All right, go ahead and do this on the board. Go ahead and match those up really quickly for me. Good. I'm going to go ahead and pause in 5, 4, 3, 2, and 1. All right, get your mouses ready as well for attendance ticket object number 5. All good. So sinking, yes, sinking means the object is more dense than water. Floating means it's less dense. And if it's suspended in water, that means it's the same density. Awesome. Go ahead, answer number 5 in your attendance ticket. It's the same question. Match it up. I'll give you 30 seconds. Screen checks when you have number 5 saved. All right. Make sure I get your green checks, please. Andrew, Angelina, Annalise, Ciara, Dalen, Dolly, Edgar, Elizabeth, Haley, Jacob, Miranda, let's see here, Melissa, Tyson, Zoe. Thank you, Zoe. Awesome, looking good, guys. Okay, so the last thing that we need to talk about is how buoyancy is calculated. So again, buoyancy is going to depend on the object's density versus the fluid's density. So we know, all right, I'm going to give you this number. We know that the density of water is 1, so 1 gram per milliliter. And based on this, we can actually estimate the density of an object floating in that water, because if water's density is 1, then another object's density is the same as the amount that it sinks. So for example, ice has a density of 0.97 grams per milliliter, which means, take that number, 0.97, 97% of ice sinks below water, and only 3% of it floats. Smiley faces if you've ever seen this with a glass of water. When you put ice in, the ice does not completely float. It doesn't just stay on top of the surface of water. A lot of it actually sinks, yeah. So that's why, for example, if you think about like icebergs or the Titanic running into the iceberg, right? The reason that ships will run into icebergs is because 97% of it is hidden. 97% of it is underwater, okay? So again, the density of the object, that is going to be the same amount that sinks below the surface. So for example, let's think about this. An object with 0.75 density, how much of it's going to sink? 0.75, how much of it would sink? Take that same number, turn it into a percentage. How much of it is going to sink? What do you guys think? Tell me in the chat box. Yeah, exactly. 0.75. If you turn that into a percentage, that would be 75%. Exactly. Good. All right, so last one before I end class. How much would a 0.55 gram per milliliter object sink? What do you guys think? Use your polling tools. Awesome. Use your polling tools. Looking good. Yes, you guys are correct. This is going to be 55%. Awesome. This is number 6. Go ahead, give me a green check when you have number 6 answered. Green checks when you have number 6 answered, and then I'm going to wrap us up. All right, looking good, guys. And here is your last word of the day. Guys, please remember to finish your quiz as well. Remember, your attendance ticket has all the answers. Here you go. Bye, guys. Thanks so much. See you guys later. Remember, finish your quiz. Your attendance ticket has all the answers.